Okay, so let's go ahead and get started. Welcome, everybody. I'm David Gertis. I'm the chair of the physics department, and it's really my pleasure to welcome all of you here today, especially so many students from physics and astronomy. It's great to see you here, and it's great to see you taking so many seats down front. I also want to welcome our audience joining us for the live stream on YouTube. So there is much more to the Taya Wu lecture than just the lecture. During her 4-day visit, Professor Jocelyn Burnell will be visiting with faculty and student groups, participating in lunches and dinners and meetings with different groups, visiting a class, I think, tomorrow in astronomy. On Saturday, she will deliver the national keynote address to the Conference for Undergraduate Women in Physics, which is taking place on our campus with about 200 participants, and also at other sites, about 15 or so additional sites around the country and around the world, and she'll be giving the national keynote address for that entire collection of conference attendees. Making all this happen smoothly takes an awful lot of work behind the scenes, starting sometimes a year in advance. So please join me in thanking some of the people who made that possible. Carol Raybuck and Holly Wanty from the chair's office. Thank you. The AV and technical support staff, and especially the large group. There's too many of you to name individually, but you know who you are, who have helped organize the QWIP conference. And that process has actually been going on for several years. So please know that that is very noticed and extremely appreciated. Thank you all. And Jocelyn, thank you for your generosity and your stamina in doing all this. So first, let me say a few words about the Taya Wu lecture and Taya Wu himself. This lecture series was endowed by Dr. Taya Wu's friends and admirers to honor his remarkable life and legacy as a scientist and a teacher and a national leader. The Taya Wu lectures began in 1992 with a lecture by the Nobel laureate C.N. Yang, who had been a student of Dr. Wu. Indeed, Taya Wu's most enduring legacy may be the generations of students that he mentored and influenced, both directly as a teacher and indirectly through his many influential textbooks on physics. Dr. Wu was born in China in 1907. He earned his PhD from the University of Michigan in 1933. His early work predicted the chemical properties of transuranic elements before they were discovered. And over the course of the next 6 decades, he carried out his research in the US, in Canada, and in Taiwan. In Canada, he led the Theoretical Physics Division of the National Research Council. Then he returned to Taiwan in the early 60s, served as president of the Academia Sinica, which is the equivalent of the National Academy of Sciences, from 83 to 94. And he continued lecturing and teaching into his 90s. His legacy as a teacher endures today through events like this. And now it's my pleasure to introduce this year's Taya Wu speaker, Professor Jocelyn Burnell. She grew up in Belfast, Northern Ireland, and earned her undergraduate degree in physics from the University of Glasgow. Then in 1965, she went to the University of Cambridge to begin her graduate work in radio astronomy in collaboration with her thesis advisor, Anthony Hewish and Martin Ryle. When analyzing the data that she from the radio telescope that she built for a whole different purpose, to study quasars, and this is often how important discoveries in science are made, which is, by accident. She noticed an anomaly, a source of very regularly spaced radio bursts that turned out to be the first detection of pulsars, rapidly spinning collapsed stars with more than a solar mass worth of material packed into an ultra-dense ball about the size of Ann Arbor. This discovery opened up a whole new field of astronomy, which continues to be at the forefront of astrophysics, and that's the story she'll tell us about today. Her discovery also earned the Nobel Prize in Physics in 1974 for Hewish and Ryle, but not for herself, one of the more infamous episodes in the history of the Nobel Prize. She subsequently worked in many roles in many branches of astronomy, in many cases part-time while raising her family. Her career has taken her to many universities throughout the United Kingdom, and she's held a number of leadership roles, including President of the Royal Astronomical Society, Dean of Science at the University of Bath, President of the Royal Society of Edinburgh, and most recently as Chancellor of the University of Dundee from 2018 to 2023. She's received far too many awards to list them all, but they include being elected as a Fellow of the Royal Society, the Royal Society's Copley Medal, and the Special Breakthrough Prize in Fundamental Physics. She appears on a 50-pound banknote issued in Northern Ireland, highlighting the contributions of women scientists. She holds the title of Dame Commander of the British Empire, which is the equivalent of a knighthood. And so one of the questions I had for Jocelyn was, how do you address a Dame Commander? Is it? She said, just Jocelyn is all. She's also received many honorary degrees, including an honorary Doctor of Science from the University of Michigan in 2008. Professor Burnell, or Jocelyn, has always used her platform to advocate for and support women in science, including by her presence at Q up here this week. And I was blown away to learn that she donated the entire $3 million from the Breakthrough Prize that she won to the UK's Institute of Physics to fund women, underrepresented ethnic minority, and refugee students to become physics researchers. So Jocelyn, it is truly truly an honor and a privilege to welcome you now to this podium to deliver the Taya Wu lecture. Thank you.
Thank you very much for that very generous introduction. And can I check, can the back row hear me okay? Excellent. You know how to indicate that you can hear me. Splendid. So this is a story from when I was a PhD student, a grad student, long, long ago. But some of the story, I think, is still valid today. And I think it's quite a good story anyway. So sit back and enjoy a story. The story starts in the early 1960s. We're at Caltech, California, and two eminent optical astronomers, Martin Schmidt and Jesse Greenstein, are puzzling over the spectra of some new objects that they've just obtained. Radio astronomy is a new branch of astronomy, detecting things that emit radio waves. To begin with, they didn't know what these things were. They're cosmic, but are they stars? Are they galaxies? Are they planets? Are they something else? And the spectra that Martin and Jesse have are the first optical spectra from some things that they weren't quite sure what they were. They were quite bright sources of radio emission, but if you turn an optical telescope to look at them, they look a bit like stars. And they became known as quasi-stellar radio sources, or quasars for short. The number of known quasars is growing. Radio astronomers are pretty good at finding them. And so the puzzle of what these things are is getting more burdensome, more acute. Jesse is busy drafting a paper trying to explain why these things, whatever they are full of the element tellurium, a well-known element. You're all familiar with it, of course. Tellurium is not a well-known element and is not usually wildly abundant in the universe. But it was the only thing that seemed to fit, or even half fit, the optical spectra of these objects. Martin, in his office, is still puzzling. And Martin suddenly thinks, that's awfully like the spectrum of a hydrogen atom, except it's all shifted towards the red end of the spectrum, bodily shifted. Could it be a hydrogen spectrum emitted by something that's moving away from us, and because it's moving away from us, it gets shifted to the red? You're familiar with this Doppler shift, as it's called. If you've ever had or seen a small boy playing on the floor. Meow! What have I got in my hand? A racing car. Yeah, somebody would probably want to specify the racing car at this moment, but never mind. A racing car. And as it's coming towards us, you hear the sound wave compressed, and as it's moving away from us, you hear the sound wave stretched out. And so it goes, meow. So 5-year-old kids know about the Doppler effect. Physicists take note. It's time you learnt about the Doppler effect. So that change in note is what we call Doppler effect. As cars coming towards us, the waves pile up, they've higher frequency. As the car moves away from us, they get stretched out, they're lower frequency, and so you go, nya. Right, back to astronomy. Things that are moving away from us will have their waves stretched out. If you're an astronomer working in the visible, that means that the wavelength gets more like the wavelength of red light. That's longer wavelength, stretched out waves. They've got a red shift. So Martin, instead of deciding he's looking at tellurium, suddenly wonders if he's seeing the spectrum of hydrogen with a large red shift because the thing, whatever it is moving away from us. But it's moving away at an alarming rate, the likes of which they've never seen before. Martin goes along the corridor to Jessie's office and says, Jessie, could it be hydrogen with a large redshift? Oh. Jessie's object looks rather similar. It's got a slightly different amount of redshift, but it's also embarrassingly large. Things in the universe aren't moving away from us at that speed, are they? And yet they seem to be. Martin was so shocked when he went home that evening, he said to his wife, something terrible happened at the office today. He really was shaken by the conclusion he was being driven to. He was right. These objects, now known as quasars, quasi-stellar radio sources, they look like stars, they emit radio waves, and they're moving away from us very fast because the optical spectra have these large redshifts. If they're very far away, of course, they ought to be faint, but they aren't. They're some of the brightest radio objects in the sky. So, big puzzle. By the time I moved to Cambridge, England, to be a grad student, 1965, we had a number of these quasars known, probably only about 20 at that stage. And there was a suspicion there might be a lot more of them, and my thesis advisor, Tony Hewish, had devised a way of finding more. And he just got money to do this, a grand sum of £20,000. It would be slightly more in dollars, but not a lot of money, to be honest, although it was a fair amount in 1965. And he was going to build a big radio telescope. These objects are strong radio emitters, known. These objects, the optical astronomers tell us, are extremely compact. They're like stars, quasi-stellar. He had a technique that I'll explain shortly that would pick out compact objects that were strong radio emitters, quasars. It involved building a very, very large radio telescope because another female grad student, Margaret Clark, who was finishing just as I arrived, had been doing a survey of the sky for radio-emitting things in the sky and noticed that some of them showed quite strong jitters in their brightness. And the things that showed this jitter or scintillation were the objects that they believed were extremely compact and were these new quasars. Margaret wasn't in a position to follow it up, and Tony built on her idea and said, well, we could find more quasars if we looked for objects that showed this twinkling, this scintillation. Okay, we might pick up other compact radio objects, but most of them would be quasars. So he's got money to do a survey of the sky for quasars. but he has to be looking for things that change their brightness rapidly. Means they're observing with very short exposures, short time constant. Means the signal to noise is not good, so you need a massive radio telescope to compensate for that loss of signal to noise. And I turn up and through a certain amount of negotiation managed to join that particular group of Tonys. He's got the money, but he's got no radio telescope. Jocelyn, your first job is to help build the radio telescope. It was quite a big radio telescope. It covered the area of 57 tennis courts, to give you a feel. It's not terribly sophisticated. It doesn't have to be. For those who are really interested, it's working at a wavelength of a frequency of 81.5 megahertz, a wavelength of 3.7 meters, so from here to about that wall. Quite a long wavelength. This slide is taken near the end of the construction. I've been in Cambridge 2 years, and I'm part of the construction team. I'll show the telescope itself in a minute or two. Typical of life, summer and winter, working outdoors. What we're actually doing here is testing the plugs that I have put on this low-loss cable, plugs and sockets, to make sure that I've made good contact. Low-loss airspace cables, you can't coil it up. One end of the cables are here, the other end are in that little red and white hut, where I sat the other half of the winter putting the plugs on that end of the cables. And my technical assistant, Don Rolfe. This is the finished radio telescope. You probably haven't seen many radio telescopes like this, but if you're working at that kind of frequency, you don't need great sophisticated metal dishes or things like that. So the wooden posts are important. They keep the bare copper wires above the wet grass, because wet grass is a good electrical short. And it's wet in Cambridge. The copper, you can identify with all this lovely oxidized copper stuff. There's rows and rows of antennae that run like this, and then these loopy things bring the signal down to more copper wire, which ultimately takes it to cables, which ultimately takes it back to the receivers in the laboratory. It took a half dozen of us 2 years to build this. A lot of hammering posts into the ground. I was spared most of it, but I could swing what we call a sledgehammer. I was playing field hockey at the point. I could hit the hockey ball from one end of the pitch to the other. I got so strong. And my team would watch the ball go by and say, "Oh, Jocelyn." They never learned to start running, but anyway, that's by the way. Almost 200 kilometers of wire and cable, and about 2,000 antennae. University of Cambridge at that point had a computer. A computer. It was built using what we call valve, you call vacuum tubes. And it took up a whole room. And it had memory less than your laptop. Very few people could use it. And Tony did not have access to it. So all this work was done without a computer. The data came out on long, long rolls of chart paper, squared paper, 30 meters of it every day. And I ran the telescope for 6 months. So I had several miles, well, 5.3 kilometers of the paper. And this photograph is some of the data analysis going on. I very quickly got used to identifying the quasars, the things that I was there to find, and found plenty of them, got the number of total known quasars up to a very respectable number. But another factor in this is what I think we call imposter syndrome. Is that a phrase that's known here? Okay, good, right. I'm female. I've come from the north and west of the country. Cambridge is in the affluent southeast. The north and west is heathen stuff. Everybody in Cambridge is brilliant. Everybody anywhere else is, And okay, I've got a physics degree from a good university, but yeah, nah, you know, I'm not male and I'm not from the southeast of England. And I'm suffering from what we call imposter syndrome. And the strong temptation to run away. But I didn't. I said, I've worked quite hard to get here. I'm not going to run away, but they are going to throw me out because I'm not bright enough. However, until they throw me out, I will work my very hardest so that when they throw me out, I won't have a guilty conscience. I just know that I wasn't bright enough for Cambridge. So I'm being incredibly thorough. I am checking every centimetre of this 5.3 kilometres of paper. And I very quickly get to identify the new quasars, the things that I'm looking for. I also very quickly get to detect radio interference. This radio telescope, 53 tennis courts in area, huge sensitivity, pirate radio stations out in the North Sea broadcasting on our keep quiet wavelength. We pick up pirate radio stations. Cars were badly suppressed in those days. A car driving down the local road would give a burst of interference. Those were the main things, but actually anything electrical could give interference. And the chart recorder pens would go until the interference stopped. But I think I've got okay at identifying interference. And I come on a piece of signal a bit like this. For the technical people in the audience, this is high-pass filtered because I'm looking for the rapid fluctuations, the rapid twinkling of these compact quasars. And I'm not interested in any of the slow, drooly fluctuations. So the slow, drooly fluctuations have been taken out. And I'm left with quite a lot of receiver noise and some little bits of interference. Maybe that's pirate radio station, maybe that's a car with a badly suppressed, maybe that's somebody in a neighboring house with electrical equipment that's not properly suppressed, something like that. And there's this. And to me, they don't look the same. They look different. Here, you can see space between the spikes. You can see the chart between the spikes. Here, particularly this bit, the spikes are very, very close together. Here, the spikes go up and down. Here, they largely go up. And that's 10 minutes worth of data for any astronomer who's interested. Now, when we say these two don't look the same, what you're actually doing is called Fourier analysis. And I had a real problem with Fourier analysis as an undergraduate, so let me just pause a moment in case any of the undergraduates are in a similar position. Fourier analysis asks what frequencies are present. These ones are lower. You can see chart between the spikes. These ones are higher frequency. What amplitudes are present is the other Fourier analysis question. Well, here the spikes go up and down, but here they largely go up. So when you look at something like that and say they look different, you're actually doing Fourier analysis. Without the numbers, but Fourier analysis. And by some miracle, I remembered that I had seen some signal like this that I couldn't classify the next time I came across it. And I thought, I've seen something like this before, haven't I? Now, these charts are strips, what we call declination strips, like latitude on the sky. And when I've analysed the charts, I roll them up and I put them in a shoebox, labelled by the declination strip. So I get out the shoebox for this declination strip. And fortunately, we work in an attic. And there's a great big space along the centre between our desks. And I throw out the paper charts, or several of them, from the last time I observed that sky, bit of sky, and line them up. So that's that quasar, there's that quasar, there's that. Right, so I saw it there, and I've logged it. That's this one. It wasn't there the time before. Oh, it was there the time before, and I didn't notice it. Ah. And there's another occasion when it was there. And look, they're all at the same right ascension. They're from the same bit of sky. And they're the same declination because this is all the same strip. So I go to my supervisor, Tony, and say, Tony, what do you think this is? And he kind of says, you bloody fool. Don't think he said bloody, but you know, something like that. Stupid ass. We can't see what's going on here. It's all jammed into about 5 centimeters. How the heck are we meant to be able to see it? We need an enlargement. Well, with chart paper technology, enlargement is easy. You run the paper faster under the pen, and it all gets spread out. But I can't leave the chart recorder running at that speed, or it'll get through a whole roll of paper in about 20 minutes. And guess who would live at the observatory putting a fresh roll of paper in every 20 minutes, day and night? Not a good idea. Next best idea, grad student goes out to the observatory about this time, switches to the high-speed recording, let it go at high speed till about here, and switch back to the normal. And I did that, and the thing had disappeared. And I made high-speed recordings of receiver noise. Yippee. And then one day, it came back. And this was the first recording. The labeling was added later. The bottom line is time, 1 second time pips. There used to be a station at Rugby in England that broadcast times. And we could put them on our chart recording. And strikingly here, pulse, 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 pulse. One missing there by the looks of things. And maybe a few more here with some missing. And the period is about 1 1/3 seconds. That's very fast for something astronomical. By and large, big things do things slowly. And small things do things rapidly. But astronomical objects are huge. Can't be an astronomical object going at 1 1/3 seconds. So I showed this to my supervisor, who frankly thought I'd wired the thing up wrong. Came out to the observatory the next day and stood looking over my shoulder as I wired up. And fortunately, it performed 2 days running, and he saw it with his own eyes. And then started a very interesting period where the main thesis topic kind of got sidelined a bit while we tried to pin down what this was. It looks awfully like radio interference. Well, there's some crazy theoreticians in Cambridge. Could they be causing interference? Could maybe somebody building astronomical equipment be testing something? Could be this, could be that. We tried all these solutions, and they all turned up negative. So, no, nobody claims responsibility. So, well, it's that daft PhD student, Jocelyn, she's wired the radio telescope up wrong. What we need to do is see if another radio telescope can pick up the same signal. And there was another radio telescope at the observatory that worked at the same radio frequency, 81.5 megahertz. So, confidentially, we enlisted their support. It was aligned slightly differently from my telescope, so it looked at a slightly different bit of the sky. So this thing, whatever it was, would pass through that radio telescope 10 minutes after I'd seen it, something like that. And I very much remember that day because I was at the observatory with my thesis advisor, Tony. Robin, who was responsible for the other grad student on the other radio telescope, and his thesis advisor, Paul Scott. And the way the telescopes were aligned, mine saw it first. Fine, it was there, it was pulsing quite nicely. Good for it. Just keep going for another 10 minutes, mate. And then we all went and stood by Robin's pen recorder, and nothing happened. So Tony and Paul start walking down this long, long laboratories, I'm padding along behind them. Now, what could it be that shows in yours, but could it be, no, that won't work because, but do you think, what about? Robin stayed by his pen recorder and suddenly there's a shriek, here it is! And his pen recorder was going peep, 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 peep. He had miscalculated by about 10 minutes when his radio telescope would see it. If he'd miscalculated by about 30 minutes, the story would be different. But Jocelyn hasn't wired the radio telescope up wrong. Another radio telescope, its own receiver, is picking up the same signal. Okay, it's on the same site, so there's still issues, but it's not Jocelyn, which was, as far as I'm concerned, the really important bit. So what could it be? Well, radio interference is a real pain, pirate radio stations and all that. Even in those days, cars were badly suppressed. And Joe Bloggs driving down the road, Joe Doak, I should say, in the US, driving down the road in a badly suppressed car would give some kind of radio signal. But if it is Joe Doak driving home from work, he's getting off work 4 minutes earlier every day, and this has been going on now for a month or two. Doesn't sound like that. Pirate radio stations, yes, but they probably wouldn't broadcast just briefly like that. And it's not a fault with the equipment. But we're already seeing that the pulses are quite short, quite steep. But they're also maintaining their pulse period very, very accurately. So steep pulses imply something small. Keeping the period accurately implies large. Energy reserves implies big. So it's big and it's small. Yep, right. Another colleague, John Pilkington, let me backtrack slightly. I'm running with 4 beams, 4 different angles on the sky with 4 different receivers. And so I'm scanning 4 strips of sky at the same time, and I've got 4 chart recorders running. This is why there's so much data. But it comes in handy. John Pilkington borrowed two of my beams, 2 of my receivers, tuned one of the receivers up in frequency slightly, tuned the other receiver down in frequency slightly, and said, does the pulse come at the same time at both frequencies? If it's from a local origin, they will come at the same time. If it's from a distant origin, there's probably some dispersion, and the high frequency will arrive before the low frequency. And after many false attempts, got a positive result. The high frequency came before the low frequency. This is a phenomenon called dispersion, caused by free electrons. If we assume that the free electrons are out in space in the galaxy, if we make a guess at the number of free electrons or the density of free electrons in space, we can measure the delay between the higher frequency and the lower frequency and estimate a distance. And he did that, and it came out at a parsec. I can't remember now. Anyway, it came out to be way beyond the solar system, but well within our own galaxy, the Milky Way. So if it's way beyond the solar system, it's not interference from those other astronomers. But it might be little green men. Finding the second, the third, and the fourth of these pulsing objects was incredibly important, because there aren't 4 lots of little green men, different places in the universe, all independently deciding to signal to planet Earth using the same kind of pulsing technique. This has to be something natural. And we're pretty certain it's not radio interference, doesn't seem to be terrestrial, seems to be in the galaxy. We are dealing with some new kind of star somewhere in our galaxy, and probably quite a lot of them. In the end, I found 4 of them. The 4th one was quite interesting because it pulsed much faster than the others and put quite severe constraints on what the physical size of this thing could be. where do I go next? We wrote the first one up for the journal Nature, which, in spite of its title, is a very prestigious scientific journal in Britain, and said, we've got another few, they're in another paper. And just before that edition of Nature was published, Tony gave a colloquium in Cambridge, gave it a very titillating title, and every astronomer in Cambridge came, including Fred Hoyle, who sat in the front row. And Tony gave the colloquium, said what we'd found, gave his favourite theory of what these things were. And here I think I have to talk astronomy parlance, so apologies. Tony's favourite model was that a compact type of star called a white dwarf. These were, at that point, the most compact things known. And Tony's idea was it was a white dwarf which was oscillating and launching shocks into an atmosphere, which somehow gave a radio pulse, and each oscillation gave a radio pulse. So Tony gave this colloquium and explained that he thought we'd probably detected vibrating white dwarfs launching shocks, giving regular pulses. Well, I said every astronomer in Cambridge had come, Fred Hoyle sitting in the front row. At the end of his colloquium, Fred is the first person to speak. And Fred had a strong Yorkshire accent, which I'll do not as strongly as Fred, because you mightn't follow me, but I don't think it's a white dwarf. I think it's a neutron star. And Fred was right. Fred Hoyle was a difficult character, but boy, was he a good astrophysicist. In 45 minutes, he's heard the first of these things, and he's hit the right diagnosis. Now, okay, people were beginning to talk about the existence of neutron stars, which we didn't know about, but Fred probably did. But there is an acid test that you can do between determining whether it's something that rotates or something that vibrates, because a vibrating thing gets faster as it ages. A rotating thing tends to get slower as it ages. So, Jocelyn, keep observing these things. We want to see the change of period with time. And before very long, we could see that the period was increasing with time. So it wasn't an oscillating white dwarf or an oscillating anything. It had to be something rotating. And we now know that it was objects that we now call neutron stars, a whole star jammed into a ball about 10 miles across. Very, very, very compact. And if you compress a rotating object, it spins faster. So that's why it's going round, about once every second or once every 2 seconds. And with time, we could see that this rotating object was gradually slowing, the period was increasing. So it all began to make quite good sense. The press took interest. The sensible bit of press was a very conservative newspaper that I normally wouldn't touch. But they had quite a good science correspondent who came and interviewed us and said, what are you going to call these things? And we thought about that. We could have called them pulsed radio sources or pulsating radio sources. But pulsed implied something making the pulses, so they're pulsating radio sources. No, he says, something short. What about pulsar? And pulsars they became, named by the science correspondent of a very conservative newspaper called the Daily Telegraph. But he was a good science correspondent. So I had, by this stage, very little time left, not much of my grant money left, and I had to stop observing and write up my thesis. Tony said it was too late to change the title of the thesis, that it had to be on the scintillating quasars. From what I now know of university systems, I think I could have changed the title, but you believe your supervisor. I was determined that the pulsars were going in somewhere, so they went in an appendix. And the bulk of the thesis was on these scintillating quasars. And I'd found a lot of them, so there were a good number of quasars. But copies of Cambridge University theses are deposited in the university library. And the university library got so tired of getting my thesis from the back storeroom that they eventually started keeping it by the reception desk because people wanted to read that appendix. Pulsars today, what do we know about them? We now believe that they are a very compact star, a neutron star made largely of neutrons, spinning very fast because this is what left after a big star has exploded at the end of its life. It's the compressed core of the exploded star. The explosion itself has compressed the core. The rest of the material has gone out into space. They're spinning very rapidly because if you take a slowly rotating thing and shrink it down, it spins faster. Conservation of angular momentum. It's got a large magnetic field because it has to have, and the magnetic field is inclined to the spin axis. So here's the magnetic field. And somehow, we're still not very sure how this works, somehow a beam of radio waves comes out of each of the poles. And as the star spins, that radio wave sweeps around. And if it sweeps across the Earth, and there's a radio telescope alive, it'll pick up a flash each time that beam sweeps across the Earth. Which means we only detect a fraction of all the known pulsars, because there'll be a number whose beams don't sweep across the Earth. We now know of about 3,000, and they are all in our own galaxy, but we believe there should be others in other galaxies, and we haven't yet, I think, got the detection efficiency to pick them up, but they must surely be there today. So, yep, over 3,000 known, all in the Milky Way. They're now, some of them, also seen at X-ray wavelengths and gamma-ray wavelengths. And they are a fantastic laboratory if you're interested in very condensed matter, because the explosion has compressed the center of the star. It is very, very dense. That's why it's largely neutrons. So these are interesting laboratories from the point of view of very compressed matter. There's still a lot of debate about the interior of a neutron star and just exactly what it's made of. The radio waves that are generated sort of out above the surface, somewhere in the magnetosphere, of course, travel to us through the galaxy, and they can give us information on the interstellar medium. And they have also proved to be very good tests of Einstein's, or some aspects of Einstein's theory of relativity. And a good colleague of mine, Joe Taylor, and his grad student got a Nobel Prize for using a pulsar in a twinned with another star to test Einstein's theories. So, properties. Stars are quite massive things. 10 to the power 27 tons, something like that, all compressed into a ball 10 kilometers apart, 10 kilometers radius. So very, very high densities, comparable with the density of the nucleus of the atom. A thimbleful of neutron star material would weigh the same as the population of the Earth. There's a magnetic field something like 100 million Tesla. To put that in context, your fridge magnet is about 1/100th of a Tesla. A strong lab magnet might be 10 Tesla. And these are 10 million times stronger than that. And when you're spinning it, that magnetic field, you get a huge voltage drop. A cool 1 billion volts per centimeter voltage drop. These are not healthy places for human beings. They're relatively weak emitters of radio waves, but they are incredibly good clocks. And they're being used to test Einstein's theories of relativity. In particular, there is a double pulsar, a pair of pulsars orbiting each other, and that's being used to check out theories of gravity. Some slightly more human angles. You've got a lot of mass in a very small volume. The strength of the gravity is huge. I don't recommend it, but if you went to one of these things, mountain 1 centimeter high, It would be like climbing Mount Everest here on Earth. The gravity is so strong. And because the gravity is strong, the atmosphere, any atmosphere, is that sort of size again. Strong gravity bends light, so we can see over the horizon, well, see with radio waves, over the horizon on one of these stars. And the gravity also redshifts light. So if there were little green men, to us they would look like little red men. Gravity also affects the way clocks go. So if you went there with your best rotary watch, instead of doing 1 tick every second, it would do 1 tick every 2 seconds because of the gravity. Not only is the gravity strong, but there's a very strong gradient of gravity. So if this is the surface of a neutron star, the gravity down there is significantly different from the gravity here. And if I were coming in to land on this neutron star, my feet would experience much stronger gravity than my head, and my body would get ripped apart just by the gradient of gravity. So don't go visit a neutron star. Magnetic field, 100 million Tesla, something like that. Voltage drops, spinning, billion volts per centimeter. And for the physicists, consequently, a very, very large Lorentz force. So don't go there. This is a health warning. And all that very condensed material, that very strong magnetic field, rotates like a solid body. The pulse period we see is the rotation period of the star, so we know they're spinning, typically, 1 a second, but some of them several hundred times a second, even 1,000 times a second. If it's spinning 10 times a second, there'll be sweeping material around with it, and you've only got to go out 4,000 odd kilometers, and the stuff is spinning at the speed of light. They're relatively weak emitters of radio waves, but their accurate timekeeping is fantastic. And that means they have been used as timekeepers to check Einstein's theories. And this is a photograph of the plaque that was attached to the Pioneer's 10 and 11 satellites, way back in the early 1970s. Certain amount of fuss about these plaques, naked people. This, I think, is meant to be the hydrogen molecule. Sun, Mercury, Venus, Earth. This particular satellite that you've just picked up has come from Earth. And this tells you exactly where Earth is, because each of these lines points to a pulsar, and encoded on the line, not very clear on this slide, in binary, is the period of the pulsar. I think done in terms of the 21 centimeter hydrogen line frequency. So we're telling them where we are. But so far, no response. Looking ahead, well, we'll continue to test general relativity, the weak field bit of general relativity. We'll continue to study how material at very high density, close packing, behaves, and also high magnetic fields. I wrote this slide probably about 6 months ago, when we were still hoping that the pulsars could be used to pick up gravitational waves in the nanohertz frequency. This has now become public knowledge that they've picked it up, so they're very good clocks, very good devices for doing some fundamental physics. We're using pulsar timing arrays and millisecond pulsars. They're giving us a better understanding of material at high densities, high magnetic fields. They're going to be good at testing the equivalence principle. This is strictly for the physicists. That's stating that gravitational mass is the same as inertial mass. And we've already seen that they can be used as navigation beacons for interstellar travel. They've also been used to test general relativity. This is a famous diagram that won a Nobel Prize for Hulse-Taylor. It's the pulse period against date of pulsar that's in a binary system twinned with another one. And it basically confirms Einstein's, or one element of Einstein's, theory of relativity. And they got a Nobel Prize for that. Joe Taylor is a good friend of mine, invited me to go to Stockholm with him at the time he got the Nobel Prize, which was very, very kind of him. It wasn't just being kind to me, it was to kind of make a political point. The Nobel Prize Secretariat were really, really anxious, because it's been widely recognized that the award of the Nobel Prize to Hewish alone for the discovery of pulsars, maybe there was some omission there. And I think the Secretariat recognized that, and they were very scared that I was going to use this as a political platform. I didn't, I just was there. It smiled sweetly. And Joe Taylor reasserted that I was a close family friend. And you may want to win a Nobel Prize, but let me give you a warning. It's bloody hard work. Really, really hard work. You go to Stockholm for a week. You're doing presentations for a week, morning, noon, and evening. You're working really, really hard. It's much better to go to Stockholm as a guest of a Nobel Prize winner. That's fun. So that's my recommendation. Oh, okay, we'll do it mechanically. Right. So these things have also been used to help understand orbits. Interesting, the clicker stopped. Okay, right, well, we've got other. So to fully understand orbits, you need a lot of parameters. The first couple are relatively easy to come by. The other ones are not, but with pulsars, you've got a chance of doing it. And you can measure even things like the Shapiro delay for those who are interested in that. Right. There's also been some talk about using these things as navigation beacons for interstellar travel. Say it quickly, sounds great. Stop and think about it. You need a rather large radio telescope. So you've got to fix a large dish, not just one of your microwave dishes or, TV dishes. Really, really big, to your spaceship. And you will launch it. Well, okay, you launch it folded up and then you open it when you get out there, but it's not quite as easy as if you just say it quickly. But you get your spacecraft launched with this large radio telescope. You measure the positions of 3 pulsars, and you get your fix in the galaxy, your position. So some of that sounds slightly crazy. I'm pretty certain all the science I've talked about is solid, true, correct. But you may be thinking, this is science fiction. I promise you it's not science fiction. These things really exist, and they have these crazy, crazy properties, and they're great fun for physicists. So go be physicists. Thank you very much.
Thank you so much for sharing that incredible story with us. And we have time for some questions. So if you have a question, there are a couple of microphones there at the corners of the central section there, if you're able to make your way to those. And if you're not, I think we have a few free-range microphones, and someone can come to your seat. So we'll take some questions now. I'm a professor, I can wait all day for this. Here's a question.
I have a question. I'm a biologist, so if it's...
Can you turn it on?
Yeah. I want to say that I want to ask the question, but first say that I'm a biologist, so I know nothing about physics. But my question is that I've read that, and you mentioned that there was only one computer in Cambridge at that time. I've read somewhere that if there had been a computer, they would have missed that signal. What would you?
If there had been a computer that I could have used, it would have been a rather limited computer.
Right.
And therefore you would have programmed it to do the job that I needed doing, which was to find these quasars, these twinkling quasars. And you would have rejected all other data because it couldn't cope.
Okay.
So human eye and brain is sometimes better.
So we don't have to worry about AI.
How, with the reams of paper you had and the relatively short period of time it takes to develop a dissertation and do the research, were you able to determine the change in period with these bodies you've described as very, very stable and reliable clocks?
No, I wasn't measuring it to enough decimal places. You'd probably need about 10 or maybe even 12 decimal places to measure the change in period. But that would have been really important because that would have distinguished between a rotating body and an oscillating body. But I couldn't do it, no.
Thank you for the talk, Professor. So my question is that a neutron star, as the name suggests, should contain only neutrons and thus be electrically neutral. So how can it have magnetic field and thus emit electromagnetic radiation? Thank you.
Because although they're called neutron stars, really they should be neutron-rich stars. There's other things as well as neutrons, in particular protons and electrons. So they're not pure neutrons. They're not 100% neutrons. But they're much, much richer in neutrons than anything else we know. So there's some justification for calling them neutron stars.
Hi. If there are both like protons, electrons, and neutrons in the star, is there a way to determine the density of the entire star and like what even that would mean? Is it uniform or?
There's no way we're measuring the radius of the star. It's only 10 kilometers and it's zillions of kilometers away. So, you know, you don't see it as an extended object. You say the radius is that or the diameter is that. The radius determination is from theoretical work about what we expect for objects of this kind of density. And the consensus is that the radius is about 10 kilometers. But 10 kilometers at an astronomical distance, you know, it's like a point.
Thank you for your lecture, Professor. Just one quick question. What do you plan to do now? I mean, you made like such a great discovery. So are you like continuing anything? Or are you like resting, retired now?
Looking back, it may have been a mistake, but I got engaged to be married between discovering pulsars 2 and 3, and got married between submitting my thesis and having the viva. Do you know viva? Is that? Yeah, that's okay. Defense, right, thank you. That was the word I really needed. Which gave the examiner some issue about what name to use on the examination form, but that's by the way. And I married somebody who worked in local government, which means that he would work for 3 or 4 years for this locality, and then he had to move to that locality, maybe hundreds of miles away. And so we kept moving. We operated a system where he'd say, there's a job going in such and such a city. If I went there, is there anything astronomical? And if there was, he'd apply. And if he got the job, I'd write a begging letter. So I went from radio astronomy to gamma ray astronomy, from gamma to X, from X to infrared, and from infrared to millimeter, which nearly got me back where I started. Utterly crazy career pattern, but married women sometimes do have, because they, you know, they're the ones whose careers get interrupted by childbearing. And if you need a steady salary, you're dependent on the man for that. And so the man's career actually often drives where the woman works and what she does. And certainly in Britain, our systems don't make adequate recognition of that, I have to say. I don't know if it's better here. But yeah. So I've covered many, many wavelengths, had a lot of fun. And yeah, it's good because you can follow developments in any of those fields, even after you've left it.
There's a question way in the back here.
So my question was about, you saw these squiggles that didn't look like the squiggles you were hoping for, and, you took the interest to actually investigate, oh, is this something here? But as someone who collects data, I mean, there's always like random noise, and, there's a lot of squiggles, I suppose. And so I was wondering, were there other things that you saw in your reams of paper where you thought, oh, this might be something interesting, and it wasn't anything, or, or was this the only thing and you got lucky that it was, actually something useful?
As far as I know, there was nothing else. And I was being really very conscientious because I was quite sure they were going to throw me out. You remember that? So, I was being fairly thorough. I think there's always quite a bit of radio interference when you've got a great big radio telescope like that. We were wiped out for a while by a pirate radio station. These bands are meant to be kept clear for radio astronomy, but sometimes other people find them useful. And, sometimes natural radio interference or human interference blocks your signals as well. So I think apart from interference, that was probably the only other stuff that was there. Well, that's produced a few hands.
Yeah, you mentioned the imposter syndrome and that you experienced this yourself. Is there any advice you would give to maybe younger scientists who might experience that today, or your younger self?
Yeah, I think imposter syndrome probably affects women slightly more than men, but equally I think men can experience it. Do you understand the phrase? Yeah, people know what I'm talking about. Yeah, okay. I think probably my technique of I will do my very best so that when they throw me out, I won't feel guilty is probably the only way to deal with it. The main hazard is that you work too hard and make yourself ill. But apart from that, I'd say, if you're feeling uncertain, students recently arrived, oh, I'm not clever enough for this place. Give it a go. Do your best. You'll probably win through. You might not, but if you don't, you'll know you've given it your best. So, yeah, go for it.
And back here.
Hello, Professor. Although computers have been undoubtedly a very powerful tool to further advancement of science, do you ever get nostalgic for those paper and pencil science days?
It's certainly easier than sometimes using a computer. Computers sometimes, it's quite hard to get them to do what you want it to do. It takes a bit of work. But equally, computerizing your results, you can process a lot more data. And certainly in astronomy these days, data comes in very large quantities. So you really have to program it. Sometimes worth trying two different ways of getting the computer to look at it and make sure that both ways deliver you the same results. If you can dream up two different ways of doing it, sort of self-checking in a sense. Yeah.
Professor, thank you so much for an engaging lecture. My question is, what does it feel like to discover something completely brand new, and what were you thinking at that time, like when you think you might have discovered this brand new aspect of physics?
One of the most exciting bits for me was when Robin managed to pick up the signal with his radio telescope. That says so much about it's not a fault of my equipment. It's really something out there, way above us, the observatory. It's not local. So devising tests like that are really, really important. First of all, to justify your result, but also because it helps you realize the significance of what you're seeing and eliminate so many much more local options that aren't half as exciting. So finding good tests of your data is really important when you're doing research. And they tell you so much about what you have found or what you haven't actually found.
I just have a simple question. When we receive the signal, and how can we tell from the signal saying that it's come from the black hole or pulsar or it's a neutron, star? How can we tell it out?
If it is pulsing, like mine was, then you need to see, is it with time pulsing faster or pulsing slower? If it's something that's spinning, with time, it slows up and stops. So the pulses get further and further apart. If it is something vibrating, as it gets older, it goes faster. So it does this, goes faster, the amplitude gets smaller, but it gets much, much faster. It stops. Sorry? Black hole.
Also rotating.
Yeah, nearly everything in the universe rotates. In fact, I think we probably don't know of anything that does not rotate. Convincingly, no. So your black hole will also be rotating. Yeah, that's right.
So how can we tell how it's from the black hole?
Because a black hole rotating, as it gets older, gets slower, and it goes pulse, 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 and dies. Whereas if it's something vibrating, it gets faster and faster and faster and faster and faster. So you observe with time and see how the period changes.
Okay.
Hello, thank you for this lecture. I had a question. You mentioned when the other laboratory used their radio telescope and he was off by 10 minutes, and you said that it would have been an entirely different story if it was 30 minutes instead. Do you ever think about what would have happened if that was the case?
Yeah, I think my thesis advisor's respect for me would have diminished even more. And whether I'd have got the PhD for the main quasar work, but it would not have been pleasant because my thesis advisor would judge that I was daft.
Hello, thank you very much. I have a question. You built your antenna array for what I think was 81 megahertz or
Yes.
something at the edge of the FM band. But so for the signals you ultimately detected, what would be a more optimal frequency to design for?
But most radio astronomy work on pulsars these days is done at higher frequencies. You're absolutely right. The lowest frequently used these days is probably 178 megahertz, but they will go up, to 408 and maybe sometimes even try in the gigahertz range. Partly depends on radio interference in your environment. That quite often determines what bands you can use, what frequencies. Because you're looking for very weak radio signals from space. And if there's a local radio station anywhere near in frequency to your telescope, you've had it.
So what would be the spectrum of a neutron star, a pulsar?
Right.
Power spectrum.
Broadly, it falls with frequency, broadly speaking. I'm not sure I can give you a number of the spectral index, but generally speaking, as you go to higher frequencies, the signal is weaker. Yeah.
Time for a couple more questions. Did I see a hand up here?
So, first off, thank you very much for the incredible talk. You mentioned the pirate radio as a source of interference. How were you able to determine that that's what it was?
Listen to it.
You were able to listen? What did it sound like?
Pop music.
Okay.
We did have a small radio on site, specifically for listening when we suspected it was pop radio. Or on another instance, the government allocated to the local police force our radio frequency. They shouldn't have, it was meant to be kept clear for radio astronomy, but there was a week when we listened to police radio cars and couldn't do any radio astronomy, so we got them shifted.
I see two hands over here. Get my steps in.
Hi. I just want to know how, based off of like just the little wiggles, you can tell how far away these things are, because they're really far. How do you know?
It's very hard in astronomy to tell how far away something is. One thing that radio astronomers can do is, let me see if I can mimic this. If you've got something far away, and between it and you there are a number of free electrons not bound to an atom, then if that distant thing goes, it arrives at you as a descending whistle. And how quickly the whistle descends, given a guess of how many free electrons there are in space, gives you an estimate of how far away the thing is. It's called dispersion, and that's a technique that radio astronomers use quite often when you're dealing with some kind of pulse or burst. Or
Sorry. I loved as an undergrad, I loved your explanation of Fourier analysis. How did you know based on, I know the pulsar signal looked like it mostly had a positive amplitude, whereas the noise was sort of oscillating differently. How did you know which one was which based on that amplitude?
Oh, I'd seen quite a lot of interference by that stage. So I knew interference all too well, and this was different.
We've got time for one more question. I saw your hand first.
So in your slide, you show if they are rotating some certain way, we can see the signal. If they are rotating, orbiting to some axis, does that mean we never detect them? Or is there any other signal we can detect to know something's there?
Probably not. They have a fairly narrow beam, a bit like a lighthouse. And if it swings round like this, you see it. But if it swings round like this, you never see it. And you don't know about it. So you only see a subset, quite a small subset.
Jocelyn, thank you again so much. Let's all thank her for this talk.